On behalf of hostess, I would like to welcome first of all the participants for their time and being here, and especially also the speakers for this readiness and willingness to present and share their ideas about the topic today. So just for to let everybody know, we are going to record this meeting as it is also mentioned on the website, and this will be available to you after the event as well. So please be aware of that. In case you have questions, you can raise your hands in Teams, and I will keep an eye here so that you could unmute yourself and ask the question, or we will also provide an opportunity for all of you to ask the questions after the sessions. We are going to have 2 sessions today, which I will come in a short bit. Okay, so first, let me introduce myself. Hi, I am Nikhil Damle. I am a senior consultant at OSTUS, working in the area of bioinformatics and life science. I did my PhD in bioinformatics from India, followed by 2 postdoctoral research experiences, one at Stanford University and other at the second at the Freiburg University in Germany. Can everybody see my pointer?
Yes, we see it.
Okay, thank you. Yeah, and since 2019, I am working at OSTUS in the area of data architecture, data modeling, data visualization, and data analytics in general. So now I would like to also take opportunity to introduce us, OSTUS in general. So we founded in 1996, OSTUS GmbH. We are leading system integrators in the area of life sciences and digital R&D consulting mainly. And we work in a vendor agnostic manner, as you can see here. In our areas of expertise are 4 pillar areas that we identify ourselves with. First is lab informatics, where we streamline our workflows, efficient IT process and integration, process integration, system integration, solution integrators, etc. Other areas of expertise that we offer are data and IT strategy, data governance, where we manage data effectively, and also advanced analytics that includes data-driven decision making, machine learning, etc. And over these 25 years, we have engaged with almost all of the top 20 players, industry players in the area of life science and chemical manufacturing, pharmaceuticals, etc. And in about more than 800 successful projects, we have delivered and we continue to deliver them successfully. We are a team of more than 100 experts situated at 2 locations, 2 sites. One is in Germany, Aachen, and one is in Melbourne, Florida, in the US. So from time to time, surrounding these 4 pillars of expertise, we arrange these meetup events every now and then. And today's topic is about fair data in life science. So to give you a brief idea about why we arrange this event or the motivation, it stems from 2 different things. First is the variety and the amount of data in life science is really huge, really vast variety, heterogeneous amount of data is being generated. And on this is on one side, and on the other side, there is increasing awareness about the FAIR principles, what FAIR is. So we started asking questions to ourselves, and our experience with our customer also tells us that people are really asking these questions. What are FAIR principles? How important are they? Should every piece of data be FAIR compliant? Or what kind of data should be FAIR compliant? So on and so forth. And this was the main motivation why we arranged today's event, and we invited 2 of experts in this area, this field. One is from our own, Arna Balser. He will also give a talk on now about what FAIR principles are and their importance. And second one is Dr. Rolf Griegart from Bayer AG, Central IT of Bayer AG. They will speak. But before we move on to those talks, I would like to ask you a question via Mentimeter. So yeah, give me just 1 second. Yeah, so this question is on your screen. What are your expectations today from today's event? What do you expect to learn? You have the Mentimeter link on top of the slide, and then there is a number next to it. So when you open mentimeter.com, you will see an area where you can input this number. Please feel free to register your responses. I already started seeing learn more about use of data science in life science industry, experiences with fair principles, importance in industry discussions, implementation examples, networking, yes, applications as implementations, knowledge, yes. How Bear implemented FAIR. Wow, very specific. So far, I think the trend is to learn how are fair principles and fair practices are implemented in industry. That's really cool. Yeah. So while we are please continue registering your responses. But while you are doing that, I would also like to introduce our first speaker of the day, who is my colleague at OSTOS, Arna Balzer. He has completed his master's in biology from RWTH University in Aachen and then joined OSTOS as a life science informatics consultant. Arna leads projects in the area of data architecture and specifically reference and master data management, RMDM. He is passionate about collaborative problem solving, UI UX design, which is user interface and user experience design. And apart from work, he enjoys playing drums, singing, traveling. So please feel free to contact him. And today he is going to talk about the FAIR principles. What are these principles and their importance? So Arnav, stage is yours.
Okay, thanks for the introduction. Let me share the right screen.
Yeah.
With my presentation here and a pointer floating around. And yeah, let's jump right in. I don't need to introduce myself anymore. Thanks for that.
All right.
So recap of what we will go through in this talk is first, importance of data in life science in general. I don't think, or I think rather I'm preaching to the choir here. I think you're aware that data in science and specifically life science is gaining more and more importance. And then I will go, and this will be the main part of the presentation, over fair data principles and also bring examples for each and every one of them. Then we talk a bit about the cost of lunch and have hopefully enough time for Q&A discussion at the end. So, importance of data in life science. Let me just try to convince PowerPoint to go to the next slide. There we are. So data are all around us. You are aware that more and more people, that's the graph on the right, are getting access to the internet and thus also access to a lot of data. And of course, they also produce a lot of data, knowingly or unknowingly. There you see that, for example, North America, Europe, Central Asia, it's almost satisfied the market. So these are the people that used the internet in the last 3 months, so 80% and more. But especially East Asia Pacific, Sub-Saharan Africa, and South Asia, for example, there's still a lot of potential for growth. So you see, it's getting more and more important. But yeah, you're probably aware of that. On the left, we see some rough figures, just estimations about the amount of data created, consumed, and stored. And I think, yeah, the green bars are estimations. And the only thing that I want to point attention to is like the unit we see here. So it's zettabytes. It's not or exabytes, it's zettabytes. So that's really the kind of ballpark we're in at the moment. And this will only increase further and further in the future. So what has almost always been true is that our ability to generate data outperformed the capacity to store the data. And I'm bringing just a few examples. So next generation sequencing, if you are working in a biolab, you probably have also seen these machines. Such a sequencer can generate up to 4 terabytes of data per day if it's running continuously. If we are going in the field of physics, there's an example from DESI, Deutsches Elektronensynchrotron. There, depending on the type of experiment, we have data in the terabyte or lower petabyte range. So already a lot of data that needs to be stored at first, but at some point also processed. And if we're going to the maximum that we could find, the LHC, Large Hadron Collider at CERN, produces around 90 petabytes of data per year. But when the experiment is running, it's 1 petabyte of data, of raw data per second. So raw data, of course, means it's not yet processed. It's really what comes out of the devices. Threshold up after which you don't call it raw data anymore is kind of arbitrary. So also take that number with a pinch of salt. Moving on, I think the view on our data has drastically changed over the last 50 years. So here just some quotes, some random quotes selected together. Originally, a lot of the data was more of an exhaust of a measurement process. I'm interested in 1 or 2 data points, but the rest is just often treated as exhaust. It's more and more, because storage is cheap, compute is becoming cheaper, something that can be stored in databases and can be made available for lookup and search. It's getting more and more valuable source for identifying patterns. In this very meeting series, we talked a lot about prediction models, about artificial intelligence and so on. And the data is getting more and more used to actually make these predictions about the future, for example. And it's definitely evolving into something that we should take care of and which needs to be regulated and managed. And that's one reason for regulation. There's a particular danger concerning the privacy. You might have seen this over and over again, this metaphor of data being the new oil, like this caricature here. So it's not oil that makes the biggest profit by getting it out of the ground, but actually data, and maybe more specifically the insight you get out of the data that makes these big tech companies, if you want to call them that, so powerful. But when we're looking at data in companies, everyone talks about actually making the data an asset. Asset meaning something of value. But there was one Harvard Business Review that got this rough figure that only 3% of the company's data that they looked at actually met basic quality standards. Of course, there's a lot to unpack in there. What are basic quality standards? In the end, it really depends on your use case. And I think with the next few slides, it will get more clear what kind of quality standards we can cover by this rather abstract concept of fair. So in the end, of course, we don't want to have this bad data quality, findability, and accessibility. We want all of that to be good so that actually more than 3% meets these standards and can actually have a benefit for us having the data. So that brings us already to the main part. This is a lot of text, just a reference slide. No worries, we will go through every one of them. So FAIR are some guidelines that were developed, meaning findable, accessible, interoperable, and reusable. So attributes or properties that well-managed data should adhere to. Let's go to the first one already, findable. And then we see that all the different FAIR principles are subdivided. In this case, it's F1 to F4. And I think the F will also be what is most important in the talk that Ralf is giving later. So F1, metadata are assigned a globally unique and persistent identifier. This sounds complicated, but actually there's a simple example. If you turn around almost every book, you will find this international standard book number. And this is already a great example of F1. The source of this image also F1. F2 means the data is described with rich metadata. Rich metadata, of course, depends on the context, but for bibliography information could look something like this. So we have the name, we have the publisher, what it costs if that's available, if it is available at all, for example. Metadata clearly and explicitly include the identifier of the data. Sounds technical as well, but it's just a small thing. Where you find the metadata, you also find that identifier so that you can make the link in the end. It sounds simple, but in the end, this can be the important thing that breaks the chain of information, so to say. And of course, everything can be searched. Metadata registered or indexed in a searchable resource. If I want to find books, I can use Google Books or any other bibliography information source. So this is Findable in a nutshell. Another is accessible, and this already is a bit more tricky, actually, because it has some more technical concepts. So metadata are retrievable by the identifier using a standardized communication protocol. Sounds complicated, but every web address, almost every web address satisfies that. So this is an example of a gene at the NCBI. And we see here actually the identifier of the gene at the end of the URL and the full URL, and it resolves. The protocol it uses is open, free, universally implementable. And there's also authentication and authorization where necessary. In this case, not necessary, but at least it's encrypted. But the A2, that's actually a crucial point. And I think that's something a lot of us can relate to. Because when you're surfing on the web, sometimes you end up on these pages. So not found, or also 404 page. And actually this kind of thing is a great negative example of A2. And it's definitely not cool. So says also the W3C. So these are the guys doing the web standards. They had a campaign which was called Cool Your Eyes Don't Change. So what makes a URI cool? A cool URI is one which does not change. Period. It does not change. What sorts of URIs change? URIs don't change, people change them. And I think that's a very, very important take-home message. If you have the URI, if you actually adhere to these accessibility practices, also think of the future. If you move your data, thinking of SharePoint, which is always used, if you reorder your SharePoint, move the data within it, then all links will stay there. Don't just make a copy and create a new SharePoint. All links will be gone that you did in the past. And yeah, actually, this example I took from a page where I wanted to download the FAIR principles, which was kind of ironic. So no one is really yeah, invulnerable to that one. Another nice example for A2 that I found was this retracted article. You might have seen this one before, but maybe not the title. This is actually the article that led to a lot of people thinking that vaccines were linked with autism. So it took quite a while until this article was finally retracted, but this article is still online. So it's just A2 in quotation marks, because A2 says metadata are accessible even when the data are no longer available. In this case, the data is available, but when you visit the website of the Lancet, actually, it says retracted all over. They want to be very sure, and I think that's a good practice. Never to really break a link, and if you don't provide the data, there can be a lot of reasons for not doing that, be it license, for example, or they were just wrong. You should at least provide some information. Don't let the user stand in the dark in the end. Interoperability is also rather abstract concept. That's why I brought some examples based on my bachelor thesis, actually. In the bachelor thesis, I did some measurements, and the measurements in the beginning ended up as a CSV file. So character separated value here, that's the Excel symbol for CSV. And this file I first copied into Excel. Then I did some Excel magic there. In the end, wrote it all together, had a PDF in the end. and at some point was ending up in a publication as just a graph. So these are different examples of actually interoperability. So the data or the metadata use a formal, accessible, shared, and broadly applicable language for knowledge representation. And this is so broad and so abstract, this thing, that it really depends on the context. So for your professor who wants to give you a grade, he needs the PDF or she. So maybe printout even would be the interoperable way of giving that to a human being. If you want actually to do some calculations on the data, you might go back to the source files or create a database instead. So it really depends on the context, on what you want to do with the data, what really means interoperable. A step towards being more interoperable can be the use of standard vocabularies. Here I brought an example of the disease ontology. This is a widely used ontology in the medical field. Almost all known diseases have a number in there. And you can use this terminology, and you can actually interlink your work with that terminology. So instead of calling something something like coronavirus, you give them the DOIT link, which is a particular number. And this way you can actually include what's called qualified references to other metadata or even to other data, and thus make your work more interoperable and also increase the chances that it will be reused one day, or that you yourself will actually reuse it one day. Reusing things myself is a good guessword here. So I brought an example of some scripting that I did, not production code, just something that I had to run once so that I didn't have to do it in Excel. And yeah, sometimes find these comments in there, something like that. So good luck, future Arne, trying to understand that one. I did not bother including really comments. Do include comments in your code. It's always worth it. Also, do version your code so that you can also go back if something needs to be undone, for example, or even have a backup. So this is a bad example of R1. This metadata or data, however you want to classify code, is not richly described with a plurality of accurate and relevant attributes. It would be if there were like really comments describing what is happening in the code. R1.1 is about usage license. May sound unimportant for a lot of cases, but actually to be on the safe side legally, you should also worry about that, especially when you publish something. And if you want to publish it more or less freely, Creative Commons licenses are a great way to go because they're waterproof and everyone can use them without adhering to very restrictive licenses themselves. So this license is also licensed under Creative Commons. Then we have provenance. So the data are associated with detailed provenance means you make it clear how did you come to that conclusion that, for example, is in your scientific paper. So that's the reference section of every scientific paper at the end. And then we have the last one in the round here, 1.3, metadata meet domain relevant community standard. And again, it's really dependent on the use case. Domain relevant, for example, if we look at a specific genome, could be these just summary information that could give someone who wants to use that genome good information on whether they it meets their expectations with regards to N50, for example. It's a quality measure basically. So these are a lot of examples how that I came up with discussing FAIR and what it means really with examples from life science. And now about free lunch. And actually, there's no such thing as free lunch, as you might be aware. The road to FAIR is hard, paved with good intentions, one could say. So what, in a really, really simplified summary, what do I think is important when you want to go towards FAIR? So just a recap, what FAIR is: findable, accessible, interoperable, reusable, are a way to represent results, or one could even say this is a test that you can apply to your data. Do I follow that? And if not, do I want to follow that? Does it have positive impact for me? But it's not just throwing a lot of tools, policies, and standards at the thing and creating over complex processes like yet another Jira process or so. That's not really it. We really need to incorporate a cultural change for everyone who is involved with handling the data. So it starts with the people entering data or the one running the measurement experiment. And it in the end, more or less ends with the one who actually consumes the data. But of course, they are data producers themselves. So it never really ends. And everyone who touches the data has to be involved in that and also see the value of actually this verification process. Because there's also the danger of FAIR being just seen as yet another buzzword that is better ignored. Some thoughts on what a successful implementation of FAIR relies on, and we will see such a successful implementation in a moment in the next talk. So first, you have to identify and select the data assets that you want to currently manage and also the future data assets. For example, if you set up a database that should be FAIR, you should also think about how big this database has to be in the end. So will it scale over time? Or do I expect this to be already full and not to be extended? Then you also have to think of the time. So it doesn't really help if your data is FAIR after 2 years of processing and then it's out of date, or if you need it the next day. You also have to factor that in. So storing, sharing the data, processing it in time and everything. So basically the full value chain and life cycle. And you have to start to manage not just your data, but also your metadata actively. Metadata could be something like if you're handling genomes, the size of the genome, contact length, when was it produced, and so on, and ensure that that the same type of data at least uses the same type of metadata descriptors, so that not in one time you write it this way, one time the other way, and you cannot really find the needle there in the haystack. You have to, of course, have to think about legal interoperability. So this is definitely something to consider when it's about privacy. Can European data be stored in the US or not, for example, or the other way around? Yeah, and I think just go over the last two ones, and then we are through. I don't know how much time we still have, Nikhil.
No, go ahead.
Okay, then the next one, you have to assess, of course, if you are towards FAIR, because it doesn't really help if you just go on and never know if you're actually moving in the right direction. And so-called data management plans can then actually build up a kind of data-driven organization so that you also internally communicate to all the stakeholders that you want to take part in the cultural change. It's always an offer. You always have to rely on the people actually committing to that, so that your plan towards the non-free lunch FAIR, but at least some FAIR data actually succeeds. And that already brings me to the end of my presentation. This is just some material for further reading and some sources. So now gofair.org, that's where I downloaded the FAIR principles, and only 2 clicks on, I saw this 404 page. So no one is really invulnerable there when it comes to fairification or even unfair data. Keep that in mind, but it's a marathon, not really just one sprint. Yeah, thank you. Do we have questions?
Thanks a lot, Anna. Yes, questions. Do we have questions? Please unmute yourself, and yeah, Ulf, go ahead.
Thank you very much, Arne. So it was a very intriguing talk, very vivid. Just as a notice, the chat cannot be used for people not in the team, not team members.
Yes. Maybe Melanie, could you check if you can enable the chat?
No, we cannot enable the chat, unfortunately.
Okay.
Then maybe
So
we use a one-off chat room in the internet or something.
No, but you can ask the question.
Importantly, at one point we will stop the recording, and then you can also ask questions if you don't want to be on the recording after the second presentation.
So my question is about the certification of the or the assessment of the certification of FAIR. How can this be done? Are there already kind of in the best case software tools that tell you whether your data is fair, or at least tick off lists?
The list, I would say, actually is this. So that's maybe a bit of a disappointing answer. There are definitely guides, and in the references, I think we have some guides that lean more towards scientific use cases, like what things to consider for every one of these FAIR principles. But in the end, it pretty much depends on your use case. One thing that I could think of, if we're thinking of checking that electronically, so automatically, would be something like data quality rules. So you set yourself rules like this and this field has to be filled for 80% of my data records, or for all of them. I make it a mandatory field, and then you could enable checks. Basically, yet another KPI, but of course it has to be some KPI that is meaningful, so that you see where am I on my journey towards FAIR. So let's say I set myself the goal, I want to annotate all my 200 genomes with at least this minimal metadata. And then one readout could already be, how much of it have I already done? And so that you get a grasp on how far are you. But I'm not aware of one tool that could actually say, okay, you are that % fair, and these are your next steps. There are a lot of tools like data catalogs and so on that can do this kind of analysis, but not aware of a tool that actually rules that all.
How do you do it in Ostus?
Thinking of in Ostus or at our customers. So there's the German saying that the shoemaker has the worst shoes. I don't think so, but we also have sometimes the issue that we want to find our own data for own purposes, and actually, we, for example, have systems on how to name files, how to sort them, some folder structures. We do not really enforce that, for at least not what I have seen. But these are the kind of things to start with. A lot of them actually derive from our certifications. So, for example, that we track who has made changes when and so on. I think these are the things that we do at our customers. It's as diverse as the industry. So we usually first answer the question: what are the data? And what should be the outcome of processing the data, and then derive basically action items from that.
Cool. Thanks for the answers, Arna. And in the interest of time, I will suggest if there are any additional questions to Arna, please feel free to ask them at the end of the talk. So yeah, thank you, Arna, once again for introducing us what the FAIR principles are, their importance, and most importantly, highlighting the change in the mindset that is necessary to implement these FAIR principles in practice. Speaking of which, we are very much delighted to have our second speaker who has already overcome this challenge, in fact, Dr. Ralph Griegart. He is from Central IT of Bayer AG, and he manages tools and services to improve fairness of the data and data management in general. Rolf received his PhD in chemistry, and since then he has been a passionate designer and manager of software products, ranging from multidimensional analytical data evaluation systems, lab informatics tools, and more recently data governance. So the latter two, as I explained in earlier, we data governance and lab informatics, even we excel at these things. So today, Raul is going to talk about how they are implementing the first and probably the most important of the FAIR principles, the findability, using linked data and semantic web stack. So now over to you, Rolf.
Yeah, thank you very much for the introduction. Let me share my screen and then we can start.
Yes.
You should be able to see it now.
Yes, we do see.
Wonderful. All right, so naturally I can only cover a very small portion of the whole variety of the FAIR standards because this is vast. This is even not really finished at Bayer. So I decided to talk about one aspect, and that is the F for findable. That's difficult enough. And just for an introduction, who are we? So Bayer is a life science company. We call ourselves a life science company. That's why it also fits so nicely for fairness in the life science area. And we have three divisions. So we have our life science spans crop science, pharmaceuticals, and consumer health. So that's why we have the motto, health for all, hunger for none. And this is really a good goal. You need to feed people in future. You need to keep them healthy. And you need just companies who take care of all this. The main point that's relevant for us in this talk is that we have nearly 100,000 employees. So we are relatively big, though we have service providers who are much larger than we are. But this means a lot of people produce a lot of data. And when we look at the history of Bayer, I won't go through all of that, but just saying we have products who are on the market for more than 100 years. And we started to produce data somewhere between the 2 points between 1951 and 2005. And when you look at that, I mean, Arne had that graph in a bit more detail, naturally, but data is growing exponentially. And data in a company like Bayer is also growing exponentially. Now, there was this marvelous question in the expectation side. What do we really want? Why would we go fair? And what's the difference to what you see in a university? Naturally, Bayer is not interested in publishing all our data. It's our internal data mostly. So we wouldn't really do that with most of the data that we have. But Bayer itself is a whole world of people, applications, groups, smaller groups, groups that don't know each other. And since we started to implement data science, we find that it makes a lot of sense to not let the data stay where they are created and where they have been used for that small group of people who are really creating them and creating them for their own purposes. We need people who have an overview over data from the whole company. We get a lot of advantage when we combine the information from, let's say, an early production stage, combine them with weather information so that we see how production of certain products match when the demand is highest, when the weather is according to where you would buy these products. So all these things require that you really know where your data are, what kind of data you have, and in the end, naturally get access to them, being able to use them, interpret them, and so on. So a couple of years ago, Bayer started to initiate the digital transformation. That is where people realized that we cannot work with silos anymore, that we need to make use of the data that we have, that data is actually an asset. And that's when we had programs like Data as an Asset, which meant all the things that Arne so nicely described. Change how people perceive data, change how people think about what you should do with data. One aspect, very small one, is to remove the data from the application where it's usually kept, that you really make the data available as their own entity and not just as something you can find and use within that one application where they generate it and maintain it. So fairness of the data is extremely important, because when you follow the FAIR principles, then a data scientist or a business analyst or a developer of an application, only then can they really do their work. Right now, it's said that a data scientist spends maybe half of the time for a project on first identifying the proper data, then getting access to it, finding a copy somewhere, getting their hands on the copy, and then analyzing the data if they are usable for their purpose, then finding they are not, and then the whole thing starts again. And that's not good. So we wanted to get rid of that. Now, we already went through this. We have departments who heavily use semantic web technologies. They use RDF data, they use knowledge graphs, and also we know that with all the data that we produce internally, most of the data that we could use is also externally in the free world. So we want things to be nicely identifiable and findable. So one of the major requirements that we got is to get F1, that we have a globally unique identifier on everything so that we know what we are talking about when we compare things. The rest of the findability, also there are some advantages that you get on the other ends on accessibility, interoperability. They are what we tackled first. We said you can have your data reusable as you like them, or interoperable or accessible as they can be. If you don't find them, well, what can you do with them, right? You can never use them. So findability comes first, and then identifying how you tackle the rest of it. So we looked at the market and looked at commercially available tools, and we found that they are not really implemented to really support FAIR. So we decided we want something that is fair in itself. And that's, again, not what the usual data governance tools deliver you. They have tools that make the data that you register in them a bit fairer, but not perfectly fair, because they lack usually the globally unique identifiers. And we wanted that. So we needed to develop something. To develop fairness, the fairness itself doesn't give you any technical implementation, but we found that the linked data principles and the semantic web stack developed for the semantic web a couple of years ago. So they were proven, they work. We know they work because companies like Google use them very efficiently. So we went with that as our technology stack to implement a tool that gives us findability. So we use URIs, they are worldwide unique, we take care of that. We use RDF as a technology, we use a triple store as the actual database. We use Sparkle endpoints to talk with the database. We use taxonomies and ontologies to configure the whole thing. So the whole shebang. The tool that we built is working with these principles. So we have a lot of data, or we call them resources. That's not just database tables and things like that. It's also machine learning models. It's clinical studies, could be real-world evidence data, can be data that we bought, data that we produced ourselves. We have ontologies, taxonomies, glossaries, or anything that holds any value and can be used can be registered and made findable. So we have the two roles or personas. One is an owner of data who wants to share the data. So we created a system called COLID. I will talk about the name a bit later. It stands for Corporate Linked Data Catalog. And naturally, you need interfaces to maintain the content and get things registered. And as you see here, it's not just a person, there's also a computer, because most of the data will be registered automatically. There's way too many things that you could do that manually. What do? We register the assets with a basic set of metadata. That is enough to describe what the asset is, what you can do with it, what the content is. The metadata fields are different depending on what you want to register. So for instance, the machine learning model has different metadata from a database data set or from a clinical study. Because, again, according to fairness, you need to use the wording of your interest group, and that's different. So people want to search for their items with different metadata. We always have a basic set of metadata that's common to all of these assets. The other thing that we need is to provide the ability to directly link to the data and more information and other things is that we have what we call distribution endpoints. And those are links to further information in internal web pages, could be SharePoint pages, could be REST APIs where you can actually access the data. Sometimes we have downloadable files like a knowledge graph where you can download a turtle file, or editors where you can then maintain the software, all dependent on what's available for the respective data set or asset. And that doesn't mean that you can access all of those, because naturally you still need to have the proper rights to get to the data itself. Findability says you need to have the whole thing searchable. I mean, that's the main purpose of it. So we have an extra search tool where then those personas who need information or data sets or assets, generally speaking, they can search there and find the data. This whole thing is also machine searchable. So we have the Sparkle endpoint that can be used for that. But we also have diverse APIs that you can use to search. You can basically create your own clients for that if you wanted to. We have one web client where normally users can do that. Finally, since we talk about semantic technologies, there is a lot of taxonomies, ontologies, and that was one of the first requirements. As I said, we need to be able to resolve identifiers to the actual information. That's one of the main requirements also of the linked data principles. And so that's what we do. We have a proxy running, and when you drop an identifier into any browser in the buyer network, then you get led to a page where you find information, what that thing means, or you get directly linked to an endpoint, because our endpoints also have their own identifiers. So that's the principles. So now what do we do with that? We don't expect that people will register their assets twice. So if people already use catalogs, then they wouldn't want to register them again in COLID. And there are many tools in a large company who have a catalog. So to give you, and I talked about the fairness of this already. So let's move on to what we have in here. So this is naturally, when I show this internally, there's tools that people recognize because they use them every day. So we have an API catalog. We have a catalog with trial data, and we have applications in a huge catalog where you have to register all the about 8,000 applications that we use internally. We have data governance tools. We have tools where we keep master data and reference data, and so on and so forth. So business has their own catalogs for something we call 360s. That's views on specific matters of interest that are predefined and nicely collected and maintained by data stewards. And they also are registered in catalogs. So this is all available, and we just link these things to Collit so that we don't need to redo that. So that's all automated. On the other end, we have external data that are of interest to buyer people. So like in the Amazon marketplace, or data exchange, as they call it, there is a couple hundred of studies and data sets for life science. And we link that as well so that we can show these data to internal people so that they don't have to go and look for that themselves. So moving on, so there's a lot of variety in here. What's also important is that you lead from one thing to another because things are related. When you find a data set, you may find, oh, that looks interesting. And then in the system, you can find, oh, it's actually linked to another data set where it's just a subset of, and that's maintained in some application. You may then also find that there is complementary information in another data set that's another subset of the original one, that somebody trained a machine learning model on it, somebody created an ontology that describes the data, and this ontology uses another one that makes use of taxonomies that are used for classification, and so on and so forth. So that gives you a nice overview. Once you find one item, you find how others link to it. And now I promised you to talk about the name. First is we were earlier than COVID. So we did get quite an internal shitstorm about why I call it Collit, but we were earlier. And then we called it an analogy to SOLID, social link data. And that's a nice thing. And we thought, yeah, that's actually a good match. Corporate link data, that matches very well. Also, we needed an icon. And there are a bird family of birds called mouse birds or colids. So we thought, yeah, that's a good match. So that's why we have this icon. And so that's always good. The last thing I wanted to talk about in theory here is Collit is open source. So already about 2 years ago, we published Collit on GitHub. You just need to search for buyer Collit application. So you found our GitHub, and you also find an article probably about Collit in Spectroscopy Europe. So that's just for your information. I would recommend to look at it. We had several other companies looking into Collit. I know it's still under evaluation with some. So maybe at some point in time, we are not the only ones maintaining this software. So I would like to spend a minute on giving you an actual idea of how it looks so that you at least have seen it. And so this is our data marketplace. This is the production system, and I have to be careful because this is recorded and you never know. So I will restrict my search to graph data. We have categories, but you can also see there's way more data types in here. You could search on anything. You don't have to restrict it. And here you have more filters on things. I explain it like if you would search for a holiday flat, you could say, I want a parking lot, I want wireless. This is how you can filter for data sets here, like information classification, endpoint types, what kind of technical endpoint you're looking for, and so on. So let's just look for materials management. And let's see what we got here. Okay, so there is an ontology, and with all the data, you find the metadata here. So you see who published it, who is the data steward for it. That's the person who knows most about it. There is an identifier that's enough to find the actual data set back. It's an ontology. There's a group of people who take care of it. And so that is kind of the least you can find here. And the description, this is not very long. This one's longer, for instance, so very different. We have another tab where you get links to other data sets. Again, I talked about links, so you can click through with that, but actually I would like to show you a better way, and then there is distribution endpoints. So here is a GitLab repository where I can get to the actual file if I have the proper credentials to do that. But as to the linked resources, I mean, you can also, when you find this interesting, you can subscribe. So whenever somebody changes something, you get a notification. There's a notification bar. You can define searches like this and let them run automatically. And when the results change, you also get a notification and things like that. Yeah, we have a tool that is built extra for being able to have a nice visualization of how things belong together. And again, this is very simple to show what's linked to what. And if somebody was so nice and already created something we call a map, then you would also find, let's say you are interested in quality management, right? Because we talked about materials management. Oh, there's already a map on that. You will also find that there. So you see, we have a lot of data and ontologies that are linked together, and mostly ontologies are used to give people some information about how the data are to be interpreted. So you see here, there's still more links that you can then go and open more, or you can just say, all right, let me show the details here. And again, distribution endpoints. And this is another example where we have an overview in this system, but you can immediately click on the tool and get a link to a data management software, data governance software, which is used by our data steward, which provides a lot of extra functionality where you can go into each detail, where you can also manage data quality with specific automated tools and so on. So this is this is the first small glimpse into what we have here. All right. I think that's just about in time to finish up. Any questions?
Indeed. Maybe if, are there any questions? Or we could also stop recording, and if people want to ask any specific questions, that's also fine.